Wonderful. Thank you, everybody. I'm Justin Johnson. I'm an associate professor in the Department of Applied Economics, and I want to build on the amazing set of talks and presentations we've had, and go towards how economics and how the economy also fits into this broader. I want to talk today about the economics of resilience and integrating circular thinking into the living Earth twin. Perhaps if I came up with a different title that would reflect what I would have presented on after hearing all this stuff and after doing all the Googling of exposomics and everything else that everybody's talked about, I might have labeled the talk A Vision Towards Understanding Exposomics with a Digital Living Twin. And so, as we've seen, we know that economics is relevant here. The economic conditions, the consumption activities, the built environment, these are all things that build what we are exposed to. But there's a conflict, and that's that the provision of consumption goods that are coming out of our economic activity have impacts on other layers of planetary health. And so to put it simply, at the global scale, economic activity risks pushing past planetary boundaries. So thank you, Teddy, for a wonderful introduction. I can skip part of this, so I'll summarize it down into, yes, we are past 6, now apparently 7, thank you. Planetary boundaries, here's the status of when we were past 6. The conclusion, though, from my perspective, thinking about how this relates to the economy, is that we are in uncharted territory, and that's problematic. One way of expressing this that has become popular among some corners is that we're entering a new geologic era called the Anthropocene. And this is one in which humans are the dominant force on our Earth systems. Funny side note, for a lot of technical reasons, many would argue we're not in the Anthropocene because you can't detect it yet in the chemical signals I won't get into that. But what I will say is that this is something even The Economist has picked up on. And so when The Economist reports on something, welcome to the Anthropocene, it's really hitting the prime time people who may not focus on just the physical definitions of different geologic eras. What I want to note, though, is how lucky we've been. This is a graph here of about 100,000 years before the present, and it's showing Earth's surface temperature. I've circled the last 15,000 or so years. That's called the Holocene. And number one, we see an elevated temperature, but much more importantly, actually, we see a dramatic reduction in the variation of temperature. There are not these gigantic swings going up and down. And that nice little stable Goldilocks zone, as it's often called, is the only world in which we've had big civilizations or agriculture or really important things like this. And so when we're going into a new geologic era, it strikes me as we should be a little nervous, leaving the friendly confines of that Holocene that's treated us so well. Also from our Stockholm resilience friends, they've charted it this way that I find really useful, is our planet here. We're moving through time, coming out of the screen here in this case. And as we go from the Holocene into the Anthropocene, we have options for how we might do things differently. Like, what amount of emissions will we have? Could we follow Earth system stewardships or practices, or just continue on our existing approaches? What I like about this is it puts the planetary thresholds right here in a graph that shows that our decisions now are going to determine what equilibrium we get to going into the future. And so that's just another way of saying we don't want to cross those planetary boundaries. We want to find out a way that we can push the system towards that stabilized Earth. Okay, so we're in uncharted terrain. But what's the problem? I'd argue that we have no adequate navigational system to help us figure out where to go and what to do. This is kind of depressing, right? But to me, the past here does provide important perspective. We've faced challenges like this in the past, and one of which that economists spend a lot of time thinking about is the Great Depression. We built tools that served as a navigational system to get us out of the depression, which was fundamentally characterized by problems of underconsumption. So some of those tools that we created, systems of national accounts, those that are responsible for even defining GDP. One that's near and dear to my heart is we came up with something called computable general equilibrium model. And I'll talk more about that, but with just a very basic understanding, that's the idea that we have a circular flow of resources and finances, and is underpinned by the concept of supply and demand. And these were very useful for figuring out how can we manage our economy essentially to increase our consumption coming out of the Depression. The problem now, though, is we've solved that a little too well and very unequally, but in aggregate, we do produce a lot more. The problem then becomes, in this context, one of not underconsumption, but overconsumption or overproduction. The challenge that we're facing then, and this is the fundamental reason why we are surpassing our planetary boundaries, is that this threatens to undermine the critical natural capital and ecosystem services. So I snuck in a couple of words there that are really important to me in my research. As an economist, I'm looking at, yes, sustainable human well-being, but one that leverages two specific concepts. The first being natural capital. And this is just Earth's ecosystems and biodiversity that are the physical, in many ways, basis of sustainable human well-being. And then the second one is ecosystem services, which are just the flow of valuable benefits, often expressed in monetary terms because, economists, hey, but the value that humans get from this natural capital. This is really critical to include for a lot of reasons, but one of which Teddy mentioned very well, I thought, was that the question of equity is absolutely critical, and the consumption of natural capital and how we benefit from ecosystem services is highly, highly unequal. This has gotten environmentalists into problems in the past, advocating policies that maybe protected some species, but came at the cost of reducing equity. And fundamentally, so greatly oversimplified, some of this comes down to the conflict between those who want to reduce consumption and those in especially developing countries who want to increase consumption. There's still global inequity among many other types. One framework that has emerged that I really like is this one here called donut economics. And this builds on the planetary boundaries. And in fact, that's the outermost circle here. And you can see they have the same metrics that we saw in the planetary boundaries framework. Kate Raworth, in her 2017 book, and just very recently in a New Science article, talks about that as the ecological ceiling here coming around on this. What she adds, though, is that this alone is not sufficient to say that you're doing okay. Actually, it is, because if we're outside of it, we're definitely not doing okay. But let me not be technical for a second, and instead say that it's leaving out an important thing, a thing that is necessary for understanding equity, and that's that we, yes, don't want to surpass ecological ceilings, but we also want to make sure that everybody equitably is above the social foundation. And this involves consuming resources like water, food, having shelter, education, a lot of things that come from economic activity. And so we want to, in this framework, neither overshoot the ceiling nor have a shortfall on our social foundations. And hence the name donut. The idea is staying in the donut, also called the social or the safe and just corridor, is a good metric for how we can plan our future. And I love this framework, but it absolutely drives me nuts sometimes because it doesn't answer what I care about, which is, okay, so what do we do? It's one thing to have a nice set of indicators, but that by itself doesn't say what should we do in terms of policy to try to keep us in that safe and just corridor. And that's what my research very focused on of late, which is building detailed models that will help us figure out how to stay within the safe and just corridor. We've been calling this Earth economy modeling. And this builds on the idea that economics has a set of really useful tools that describes consumption and production. And economists really love this idea that they think about the economy in general equilibrium, where they think about all the factors interacting. But a key thing that we argue is that it's not general enough in almost all cases. We need a more general equilibrium in which the economy is embedded in the earth. One of the ways we've been doing this specifically is working with the Natural Capital Project. This is an organization that the University of Minnesota is a founding member of. It's currently hosted at Stanford University. Stockholm Resilience Center is a part of it. What they are known for is, among other things, creating a tool called INVEST, which is the integrated valuation of ecosystem services and trade-offs. It's an open source software system that estimates the value of a little over 20 ecosystem services using spatially explicit, high resolution, process-based calculations of where nature provides value to humans. And I also want to reference a spin-off organization in my home department, the Department of Applied Economics. We have created NatCap Teams, where Teams is the Earth Economy Modelers. This is a brand new research center. We just had our 1-year anniversary, and we are focused on connecting ecosystem services in just the way that the Natural Capital Project does, but explicitly to economic models. And so our goal is to start to build this model, this digital twin. You can see where I'm going. And that's, we're going to have the economy. It's going to have the basic things that economists built and that are useful for making predictions, such as how consumers and producers produce goods and services. That's the circular flow diagram you learn in Econ 101. But we don't want to stop there. We want to embed that in the broader context of having the biosphere as the source of much of the inputs to the economy, but also just the enabling conditions. And in particular, we want to express Earth systems, not just in general terms, but with high resolution depictions of the Earth. We have great data from satellites now, remote sensing sources that give us increasingly high resolution and frequently photographed pictures of what's going on in the landscape. And this is a very useful input both to Earth systems models for calculating ecosystem services, but increasingly also as an input to the economic models. The critical point, and this is where we have spent, I think, most of our time, is noting not just that the economy is embedded in the biosphere, but that it's linked in both directions. Most people, when they think about environmental protection and its connection to the economy, probably think about the impact side. That's the drivers. That's traditional environmentalism, where we see that economic activity does bad things like deforestation or pollution or all these others. Those are very important, but as we get closer and closer to or have surpassed planetary boundaries, the second one becomes increasingly important, is that economic activity itself is dependent on nature. One thought exercise I often like to think about is, what would the GDP be if we were on Mars? Pretty close to zero. Maybe some people could survive it. Maybe in 100 years, it would be more significant. But at the moment, if we didn't have the natural capital present on Earth, like oxygen and such, the economic activity of that society would be essentially zero. And so that's just a sort of over-the-top illustration, but economic activity itself is dependent on ecosystem services and natural capital. The reflections that I have on today are that we need to consider broader planetary health and exposomics. That's something we haven't yet spent much time on, but that fits within this overall framework. It would be adding, a micro lens or other additional details to this framework, but this all fits together towards the idea of creating an Earth economy model, or maybe something that is a digital Earth thing. This is kind of a new topic. We just shout out here. We just published this in annual review of resource economics. So that's the graphic designer's version of the one that I made in PowerPoint. Um, but the key point is that we really need to understand all of these impacts and dependencies to be able to have an adequate navigational system going into the future. As a good academic, I would have to note that there's a lot of other models in this space. We're not the first. But what I would argue is that there's oftentimes a trade-off. Some will have very high levels of spatial resolution and physical detail. So we've actually enumerated them there on that axis. Then in the econ world, on the vertical axis, there are models of varying levels of economic detail and specificity or complexity. But it's really in this direction that the frontier exists. And this is where we think Earth economy modeling needs to go, is to embrace essentially more powerful computers towards having both the environmental and the economic complexity. Okay, so that's Earth economy modeling. We've created one specific model that we think fits into this space, and we call it GTAP Invest. It was recently published in 2023 in the Proceedings of the National Academy of Sciences. We have a bunch of forthcoming articles on it, but basically what it does is it takes the most commonly used economic model, which is called GTAP, the Global Trade Analysis Project model, and couples it with the most commonly used ecosystem service model, INVEST, that I already mentioned. The linkage, though, as you guess, is in both directions. We think about how the economy affects ecosystem services. A lot of that is through land use change. So we have a model of that. But then also, how do changes in ecosystem services affect economic productivity itself? And so there's way too much complexity. This is a modeling paper. I am a coding nerd. Please check out my GitHub page. But the idea is that we're going to essentially glue these models together so that the changes in one feed into the next model and goes back and forth, where we quantitatively calculate how do these drivers affect the environment, and thereby how does the environment affect the economy, and project that into the future. The two parts of the model that I will emphasize is first the GTAP model itself. And this is useful because number one, it's the most widely used framework in the world for trade policy analysis, and frequently all sorts of other types of analysis like climate change, land and water use. One that's specific to research here in Minnesota is biofuels. What would the impact on prices of food be if we diverted a bunch of corn from consumption by humans or cows into our cars? Well, this is the type of model that is used to answer that question. Maybe more prosaically, it's also a model that has become the common language used by central banks, finance ministries, other key decision makers when they're analyzing a policy, and simply using their language, we've discovered, is very effective because they sort of automatically get and have a fair amount of buy-in into what we're saying. The important part that we do is we take an extended version of GTAP that explicitly shows that the impacts of economic activity and how they play out in things like climate change or land use change and many others. But this is basically the impacts side of that circle diagram. The other side is dependencies coming from INVEST. And at the current state, we have 6 ecosystem services that we can calculate at a global scale, which are sediment retention, climate regulation, pollination of crops, timber production, coastal protection, and marine fisheries. There's a whole lot of work that goes into actually computing those. But what I would highlight is that it's one thing to calculate the ecosystem service. That's sort of the first column. The really big part of the work that we had to do was to think about how do you translate a change in the biophysical state of the ecosystem service provision to some sort of impact on the economy. So some of them are pretty straightforward, like pollination. If you have less pollinators nearby a pollinator-dependent crop, that crop won't be as productive. And so an economist can see how that would fit into the production function. We solve our model and see what actually happens in terms of losses. But this is one of the frontiers, is filling out this set of linkages with more linkages and more detail in the science. So it's an agenda too. I'm going to skip my friendly animation, but other than to say that we do calculate this at it's really detailed process-based models. And so, for instance, we track how nutrient is retained or sediment is retained by different land use types and keep track of what's the flow path as it goes towards the stream, and calculate important things like what's the transport and retention of sediment and nutrients, and how does it flow eventually towards the stream. And all I'll illustrate here is we calculate this at scale. And so we calculate that flow path for each pixel and then iterate over all the pixels. And so not too surprisingly, a lot of the actual day-to-day work we do is with computers. How can we make such a big computation happen? And so it's actually quite new that we've been even able to calculate ecosystem services at the global scale. And so here's sort of our coming out paper, like, hey, we can do it. Rebecca Chaplin-Kramer, 2019 Science, and then a series of articles going after that. But all of these papers started to build out the evidence base that when you look at different projections of land use, as illustrated here, we have on the top would be an example of business as usual and the land use that is present there versus some sort of alternate scenario like a conservation scenario. The first thing you see is you can't see a darn thing. That's because you need to zoom in. And so when you zoom in, you can start to see results of how does the provision of, say, pollination services differ spatially. And so here's Ghana, and you can see different land use trajectories have massively different degrees to which pollination contributes value to the economy. And so just quickly talking them through, we do have our pollinators, carbon storage, marine fisheries, coastal protection, and here I also include water yield. But the real results are not just those ecosystem services, but what are the impacts on the economy then? And so we have a number of pieces which I could spend all sorts of time talking about, but I want to highlight a few of the important things. The first one, and this has come out critically through all sorts of different studies, so it's quite consistent, is that nature matters, but especially to low-income countries. And so, again, this is coming back to that equity point. It's not too surprising. Low-income countries tend to rely on nature more. They, in fact, have a lot more nature still, haven't depleted it as much. But also common goods like access to forests and fisheries and things like this tend to be more important in those locations. And so it's sort of not too surprising, but when you run the whole GTAP Invest model and you look at a policy that has degraded ecosystem services versus assuming somehow ecosystem services don't get any worse, we see that there is a massive reduction, first off, in the total amount of GDP produced, so 2.7 trillion. But more importantly than just the fact that nature matters and has big dollar values is that it's unfair. You can see that low-income countries lose much more than high-income countries. So, in other words, it's important. The complementary finding we have is that in addition to nature mattering, especially in low-income countries, fortunately, there's also policies that we can implement, and those also benefit low-income countries disproportionately. And so that was the key finding of our PNAS article, is that investing in nature can improve equity and economic returns. And so we looked at a portfolio of different policies, including different payments for ecosystem service programs, different approaches to repurposing agricultural subsidies, which result in too much agricultural production, repurposing that to other things like research and development, and also the transfers among countries in order to see what are the sets of policies that improve outcomes for both the environment and the economy. And this is where I think we start to see more clearly some of the conflicts. And this is an illustration of something that is very important from the equity perspective. When you start thinking about policies that protect large amounts of land, so a commonly discussed one is called 30 by 30. There's also half Earth. These are essentially large-scale conservation activities that expand protected areas. And so basically what we have here is current protected land is green, and we are identifying a possible policy to achieve 30 by 30, and that's adding the purple and magenta land to it. But the problem is some of that new protected land is on locations that have existing agriculture. And that's all the areas that are in orange. And so we modeled what the impact of this is using our GTAP Invest model. And essentially what we're doing is to say, okay, you have an economy, there's less land as an input to production. We actually know where it's happening, at least in this proposal, and we recalculate our model with this land not being available. And the key finding is, and this builds on the results I just showed from the PNAS article, is that protecting ecosystem services and those policies, that indeed was good. And here's just that same result. I guess you can't really see my cursor very fast updating, but that green bar right there, that's the same result from the PNAS article showing that low-income countries benefit the most from these nature-aware policies. Problem is when you then consider what are the costs of these more ambitious land protection policies like 30 by 30, that has huge costs, and it more than offsets the benefits that we got from the other policies. At the global scale, what do we see? They almost exactly cancel out. And so at the global scale, you don't have to worry about it too much, but there are massive equity concerns to think about when low income countries are taking the disproportionate share of the impact. So I want to end with just two ideas of going forward on this. First is just expressing the idea of why even connect economic models. What's the point? And the idea is that there might be, and often we can show that there are, win-wins present for both the natural quality and the economy. And so here's a graph. This is actually a Pareto frontier where what we're saying is we can think about on the horizontal axis some sort of economic indicator like revenue, and on the vertical axis any one of many possible environmental indicators. And the key thing we find is that compared to the current landscape here, having differently configured landscapes results in some configurations, all those points F through B, improvements for both ecosystem services and the economy. But really the question is not, do those exist? But it's how. How do we come up with the policies that transition from that interior spot I to those ones that are win-wins? And that's the role of Earth economy models, is to try to calculate out the different policies so we have some sort of sense of what might work in that context. The second of two next steps that we really need to focus on is changing our metrics. This is probably well agreed by many here, but economists spend way too much time thinking about GDP, gross domestic product. It's not a great indicator of welfare. It's a good indicator of the value of physical things we produce, sure. It was very important when we were building tanks to win a war or something like that, but it's not so good when you're pushing up or past planetary boundaries. And we need new metrics, better metrics. There's lots out there, but there's one that we are working on here at the Earth Economy Modelers Research Center, which we call GEP. It's obviously a complement to GDP, but it's gross ecosystem product. And some of those things will have a little bit of overlap with GDP, like the value of grasslands and how that produces things that we might eat through livestock supply chains, but also all sorts of other regulating ecosystem services that don't have a price put on them, at least not by default, such as clean water from wetlands. So we are close to releasing a new global data set of 38 GEP metrics, basically to do an improved accounting of our natural capital project. But then just to conclude, in this context here that we're discussing today, thinking about a living Earth twin, that's essentially where Earth economy models need to go. We need to scale, and that would take many forms, but one of which would be including many of the concepts we've talked about today, especially in the last presentation about planetary health. But on the flip side, we also need to remain computable with increased detail. This, going back to the donut diagram, my only problem with that is I love it as a concept, but you can't calculate it. It's not a model. I like to have a quantitative thing that you can play around with different policies. So we need to keep that computational ability. So I just have a call out to a new research center, not even new anymore. It's been around for a number of years. AI LEAF, the AI Institute for Land, Economy, Agriculture, and Forestry. Some of you are involved with that. It's formerly called AI Climate and changed names for reasons. But basically, the idea that we have been toying around with there is we could use AI, specifically reinforcement learning models, to emulate Earth economy models and create reduced complexity approximations of these models that can scale up to be able to calculate faster, yes, but maybe more importantly, include more details like planetary health aspects. And that's where we're going. I think this is necessary because we need that navigational system to be able to navigate this really uncharted territory that we are now in. And I think planetary health will be, or integration of the planetary health will be critical to that aim. So thank you.